Hi class, before we get started, just wanted to apologize. It turns out the audio quality on this one and the next videos on bearings didn't turn out so well. I'll try to make sure that in the future the recording sensitivity is adjusted properly. Okay, on to rolling contact bearing analysis. Let's learn about how bearings are rated for their life and load. If we have 50 ball bearings and they're all rotating at the same constant speed, we apply a constant radial load 1,000 pounds to each of them. And what we're going to be interested in is when we apply this 1,000 pounds, how many of the bearings have failed by a life of 1 million revolutions, 10 to the 6 revolutions. And so we might measure that, do that experiment, and we find that this many of these bearings have failed. I guess that's 28 because I've got 50 here. 28 of the bearings have failed. All right. At 750 pounds, only 10 of them have failed. And if we lower the load further to 500 pounds, only 5 of those 50 fail. And that is a special number, 5 of the 50, that's 10%. That is what manufacturers shoot for when they're specifying loads and lives, right? They pick a life, 1 million cycles typically, and they find the load at which 10% of the bearings fail, and they call that the dynamic load rating. You can see here this rating, designated as CR, this is from the Timken catalog, we call it C10 in the book, is defined as the radial load under which a population of bearings will achieve an L10 life of 1 million revolutions. So they've set L10 to be 1 million revolutions and found the load at which 10% of the bearings will fail before they reach that life. So C10, 10 referring to 10%, it's also known as the CR or rated C, that's the dynamic rated load, is the load at which 10% of the bearings fail before reaching 1 million revolutions. And so our 500 pounds force for this bearing, that is our C10. Okay, so let's answer an example problem. We have this bearing from McMaster-Carr. At what load will 10% of these bearings fail before they reach 1 million revolutions? So let's zoom in on this information here. This one's really easy. 10%, we already know that that's a special number for us. 1 million revolutions, that's our L10 life. So whatever this dynamic load rating is, that is the load at which 10% of the bearings fail before they reach 1 million revolutions, by definition. So by definition, 2,150 pounds is our answer to this question. Okay, so a second example. We have a radial load of 4,300 pounds, and it's applied to the center of a rotating shaft that's supported by 2 bearings. 2 of these bearings here below. What is the reliability of the system for a life of 1 million cycles? So we've specified the load, we've specified 1 million cycles, and we're interested in now the reliability of the system, or what percentage of the cases, if we did this 1 million times or 1 billion times, what percentage of those cases would the system survive under these conditions for this life? What's the probability that a bearing will fail before the shaft rotates 1 million times? That's the complement of this question. If we decide that the system has a reliability of 99%, then there's a 1% chance that the bearings will fail, that one of the bearings will fail at least before the shaft rotates 1 million times. So let's take a look at that one. So 4,300 pounds force applied to the shaft. Here's our shaft. Here's our force is 4,300 pounds. And if we are supported by the bearings on either side, then each of these bearings, you can see by static equilibrium, then each of these is going to support 2,150 pounds force. Because this is in the middle, so you can do that by symmetry, or you could solve it carefully. Now, a lot of practical problems are going to be like that. You're going to have to solve for what the forces on the bearings are. There could be an axial component in some cases, not just radial, but you'll have to figure out what that is. That's all coming from statics. We're not going to relearn that stuff here, and so some of our example problems aren't going to include this step where you have to find the loads, because You've already learned that stuff. You've already practiced it a lot. We're just thinking about bearings right now. So in this case, we did it. We found that the force on each bearing is 2,150 pounds. And you might say, oh, look, that is the dynamic load rating. And the dynamic load rating is the load at which 10% of the bearings will fail before they reach 1 million revolutions. So you might think, oh, then the reliability is equal to 90%. There's a 90% chance that a bearing under that load will will survive a million revolutions. You might think that the probability that a bearing will fail that a shaft rotates a million times then would just be 10%. There's a 10% chance of failure. That would be true for a single bearing, but I've been tricky here and I've given you two bearings. And both of these have to live for a million cycles in order for the system to survive. So each of these bearings individually has a 90% chance of surviving. We know that the reliability of this bearing, I should probably change my letters here. Each bearing has a 90% chance of surviving. So the reliability of the system, it requires both of those things happening at the same time. So the reliability of the system overall is R, 90% chance, of 90% chance is 9 times 0.9 is equal to an 81% chance of the system surviving for that long. And so the probability that at least one of the bearings is going to fail before the shaft rotates a million times is 1 minus the reliability of the system. There's a 19% chance that one of the two bearings is going to fail. At least one of them is going to fail. So you can see that even if you have a relatively high reliability on your bearings, then you quickly get to a situation in which there's a pretty good chance that one of them is going to fail before this happens. And that's why sometimes you are going to need, and we'll talk about later, reliability is better than 90%. As you increase the complexity of a system, the probability that something will go wrong tends to go up. All right, now we have a different question. At what load will 10% of these bearings fail before they reach 1 billion revolutions? Okay, so we know that at a load of 2,150 pounds, 10% of the bearings will fail before they reach 1 million revolutions, but at what load will 10% of them fail before reaching 1 billion revolutions? It turns out that for any fixed level of reliability, so 90% reliability is what we're fixed at, then this is true, where F is the radial force on the bearing, X is the relative life. The relative life is the life of the bearing divided by the L10 life, a million revolutions. And this goes to the exponent of 1 over A, where A is 3 for ball bearings and 3 1/3 for roller bearings. This is an empirical phenomenon. It turns out that if you do a lot of tests, you'll find this to be true, that regardless of what the radial force and relative life are, they follow this relationship so that when you multiply them together with the relative life taken as to the 1 over A power, you get a constant number. It's always the same. And this is going to be true whether it's a load that you apply or if it's the rated load. So this lets us solve this problem. Let's go ahead and solve this one. At what load will 10% of the bearings fail before they reach 1 billion revolutions? Let's start out by writing what we just learned. That the force times x, the relative life, to the 1 over A is equal to a constant. So in one case, we know that the force is equal to, when the force is equal to the rated load, then the life x, which is the actual life over L10, well, the life at that rated load is going to be L10. At the rated load, it's going to survive a million cycles. That's by the definition of this rated load. So x is just 1 in that case. And 1 to the 1 over A, well, it doesn't matter what 1 over A is. it's going to be 1. 1 to the 1 over 3 is equal to 1. So in this case, x to the 1 over a is equal to 1. So this has to be equal to, if it's constant for all loads and life combinations, then this has to equal C10 times 1. So that lets us find what, well, we know what the life is in this case. We know what x is, 1 billion revolutions. That's going to be 1,000, I guess, is the relative life, 1,000 times L10. We need to solve for the force at which 10% of the bearings is going to fail, because this is again assuming a constant reliability of 10% fixed reliability. All right, so we can do that. We say F is equal to then C10 over x to the 1 over a. C10 is equal to 2150 pounds. X to the 1 over a, let's figure that out. X is equal to the life that we're talking about over the L10, 1 million. We're talking about 10 to the 9th over 10 to the 6th is 10 to the 3rd. We're taking that to the 1 over a is the 1/3 power. To the 1/3 power, that's just going to be 10. And so we have this divided by 10, and that is 215 pounds force. So at a load of 215 pounds force, 10% of the bearings will fail before reaching 1 billion revolutions. And so that's how you use this relationship that F times the relative life to the 1 over a is constant. That constant is, by the definition of C10, it's equal to C10, you'll find. And so sometimes you'll just see this written as C10 is equal to Fx to the 1 over a. And this could be useful if you know what force you want to operate at and you know what the life is that you need to get. Then what rated load are you going to need to look for in the catalog in order to find yourself a bearing that will fit that role? But in this case, we have said, oh, we know what C10 is, we know what our life that we need is, what force can we apply?